Within our paper, a benchmark dataset for repetitive pattern recognition on textured 3D surfaces, we present an annotated dataset of ancient pottery artifacts. The surface paintings exhibit textual and geometric patterns of different complexity and different levels of repetitiveness. The recognition and classification of such surface patterns is an important research objective in the digital humanities. However, the designing of recognition methods or training of machine learning algorithms requires some sort of ground truth. A benchmark dataset is also required to compare the performance of different detection techniques. Unfortunately, to date, such benchmarks dedicated to specific fields of research like cultural heritage are a rarity. Hence, the main contributions of our paper are the following. First and foremost, the annotated dataset of 82 textured meshes with repetitive surface patterns. These surface patterns were labeled manually by archaeologists who identified clearly definable pattern classes. In total, we are looking at 102 distinct similarity classes with a total of more than 2,500 individual occurrences. A big advantage of our dataset is also that we have real-world objects. We present an annotation tool set with an appropriate workflow which we used for obtaining said annotations. Moreover, we propose two orthogonal evaluation metrics for ranking different recognition methods. Finally, we evaluate our dataset and propose metrics with two naive sampling-based approaches, as well as a domain-related method for repetitive pattern recognition. The dataset, as well as the annotation tools and scripts for the evaluation, are provided on a publicly accessible website. In terms of similar benchmarks, there have been several related contributions to the shape retrieval contest, SHREC, in the recent years. This annual contest features a series of tracks for evaluating methods and algorithms related to 3D object retrieval. The first track dealing with the retrieval of surface patterns was the 2008 track on recognition of geometric patterns over 3D models by Busotti et al. Within this track, a dataset of 3D scanned artifacts with geometric patterns was used, and the goal for the participants was to determine whether a specific object contained none, one, or several of a given reference pattern. The track proved to be difficult for state-of-the-art methods, as none of the submitted solutions was able to yield satisfying results. In the same year, another SHREC track was submitted by Moscoso-Thompson et al. Titled Retrieval of Gray Patterns Depicted on 3D Models. This track was concerned with the retrieval of painted patterns on synthetically generated models. And finally, 2020's track Retrieval of Digital Surfaces with Similar Geometric Relief, also by Thompson et al., had a dataset with 11 different geometric reliefs. The task here was to detect groups of objects with similar geometric reliefs regardless of the object shape. For this track, machine learning as well as engineered approaches have been submitted, whereas prior yielded the best results. Our dataset consists of triangle meshes captured from real-world pottery artifacts with a structured light scanner at the Josefina Ramos de Cox Museum in Lima, Peru. The collection comprises several shape classes as jars, pitchers, vases, and more, and the objects are also attributed to different pre-Columbian cultures, which is observable in shape and painting style. We pre-process these objects such that the y-axis aligns with the rotation axis and that they are scaled to an unit cube in a 3D origin. Since we have real-world objects, they also exhibit various impairments. Those include various forms of erosion like missing fragments as well as chipped off or worn off surface parts. Other deficiencies result from occlusion and other errors in the scanning process. As these imperfections are characteristic for real-world models, we believe that they add an additional level of quality to our dataset compared to synthetically generated models, for they pose an additional challenge to algorithms operating on them. In order to obtain these annotations, we developed two interoperating tools. The first tool, labeled Sample Pattern Selection, is used to identify the pattern archetypes present on an object surface. Hence it takes a 3D mesh as input and returns a set of sample entities, one per archetype. The second tool, Pattern Entity Selection, is used for annotating the pattern entities. It takes the pattern samples, which are images, as well as the 3D mesh as input, and returns the annotation in JSON format. The reason the annotation process is split into two steps is that the annotation effort can also be split up between different groups of people. This is advantageous as the identification of pattern archetypes requires domain knowledge and should be conducted by experts, while the selection of individual entities could be generally done by laymen. The sample pattern selection features a 3D viewer displaying the loaded 3D mesh. A user can extract a sample image for an archetype by placing a set of seed points around one of its entities. Based on that, we perform a view translation which ensures that the selected pattern entity is centralized in the camera. We use a perspective camera with 90 degrees vertical field of view and calculate the distance to the object surface such that we obtain an encompassing image of the pattern with some additional padding. For each pattern archetype, one such sample image is generated. The pattern entity selection loads the same 3D mesh and also the generated sample images. As the objects in our dataset are comprised of solids of revolution, they can be easily transformed into 2D space. Hence we decided to let the user conduct the annotation on a flat surface proxy and remap it to the 3D mesh. This proved to be much easier in terms of navigation and selection. The user interface we came up with is tripartite. It features a selection list of pattern archetypes, a flat surface proxy, and a 3D viewer, displaying the annotation on the 3D mesh. The annotation process starts by loading the 3D mesh as well as the pattern samples resulting from the previous tool. Then the user selects the pattern archetype he wants to annotate from the selection list. Then he can specify a location of an entity by means of a polygon lasso, and afterwards additionally the orientation and scale of an entity with respect to the archetype sample by aligning an overlaid display. This process is performed iteratively until all pattern entities are annotated. Finally, the annotation can be exported. We present two orthogonal evaluation metrics which allow to rank different recognition approaches. They evaluate results on a per archetype level, meaning that an algorithm is provided with a pattern sample as a query and should return the location of similar occurrences in the form of a set of coherent surface areas. Additionally, each of these detections should have a confidence value. The first metric, the mean average position, follows the method presented in the Pascal Visual Object Classes challenge. Basically, we have a set of surface areas corresponding to the annotated ground truth and a set of surface areas resulting from a recognition algorithm. We pair them up greedily with respect to their intersection over union before we mark pairs with an intersection over union of more than 0.5 as true positives and others as false positives. Ground truths without a match become false negatives. By sorting the list of correspondences, we can compute recall and precision values. The final evaluation measure is the mean value over the average position of pattern archetypes in the complete collection. There are of course a lot more image-based pattern recognition algorithms than for 3D objects. At the same time, the object surfaces can be mapped to 2D space with appropriate unwrapping methods. Hence we propose an additional evaluation metric for image-based recognition methods, which operate on the planar surface representation. It's a normalized average distance in the range of 0 to 1, with 0 for the perfect solution and 1 in the worst case. To this end, we assume that we have a set of point locations of pattern entities in 2D space. We obtain those from the centroids of the annotation polygons mapped to the flat surface. Similarly, we expect the recognition algorithm to yield a set of point locations of detections. Additionally, the rotation scale and reflection state with respect to the query could be returned. In the first step, we pair up the detections with matching ground truths. With a greedy nearest neighbor approach, it could happen that multiple detections are paired up with one and the same ground truth. Hence, we use an optimal assignment which minimalizes the global distance to assign each detection to a ground truth. We then get the average nearest neighbor distance from accumulating and averaging the pair distances. Those are a function of the distance of point locations and, if given, the differences in rotation, scale, and reflection. A remaining issue is that too many or not sufficient detections could be returned by an algorithm. We take care of this overhead by introducing a penalty term which assumes the maximal normalized distance of 1 for each of the detections or ground truths which couldn't be paired up. We also conducted an initial experimental evaluation with our proposed evaluation metrics and dataset. Unfortunately, there are not a lot of recognition approaches really suited for this kind of problem, at least none which we found to be readily applicable. Nonetheless, we came up with a self-made solution and implemented two different trivial approaches. Firstly, a purely random approach, which is basically a blindfolded oracle predicting random locations on the object surface, together with purely random rotations and scales. This we refer to as random selection R&D, and it should just serve as a sort of lower baseline. The second one is a bit more sophisticated. Similarly to the random selection, we generate an initial set of random seed points. At those we compute the absolute difference of query image superimposed on the object surface in the RGB color channels. Subsequently, all predicted locations are ranked by this distance metric, and only the top ranked detections are returned. This we refer to as random local XOR, RLXOR. The third approach, repetitive ornament detection (ROD), is one of our previous works. Within this approach, we combine a sliding window XOR with the binary pattern and surface, with the assumption that patterns appear in a repetitive manner in ornament bands at isohypsal positions. Unfortunately, it has only limited applicability to the presented dataset, as it requires the surface to be binarized, which is not possible for the majority of objects, as most of them are polychromatic. With those approaches, we conducted a qualitative evaluation on 3 distinct objects with increasing numbers and complexity of surface patterns. On the first object we have 6 star-shaped patterns, on the second object 65 very similar N-shaped patterns in white and red, and on the third object we have 2 distinct pattern archetypes, a large face shape with 5 entities and a smaller triangle shape with 113 entities. Here you can see the ground truth obtained from the manual annotation. The orange and blue circles show the location and the extent of a pattern entity for a given pattern archetypes. The next rows show the results obtained from the random selection, RLXOR and ROD approaches respectively. From this figure we can derive 2 essential things. Firstly, that our 2 metrics, mean average position and average nearest neighbor distance, generally agree. Keep in mind that prior has a precision reaching from 0 to 1 and the latter a distance reaching from 1 to 0. The second thing we notice is that the random selection performs, as expected, clearly the worst, closely followed by the RLXOR. The ROD clearly yields the best results and is able to detect all of the pattern entities in the first object, the majority of white-colored ones in the second one, and at least a handful of both patterns in the third object. Additionally, we conducted a quantitative evaluation of the 11-point normalized mean average position on the whole of our dataset. Note that we did not include the ROD approach as it was not able to provide results for the majority of objects. As expected, the random selection is not able to come up with meaningful results whatsoever. The RLXOR is slightly better. However, it has precision values of below 0.5 for all recall levels, which is clearly too low for practical applications. Quite the opposite, as it unmistakably stresses the need for more advanced recognition methods. Our proposed benchmark and the initial dataset have ample room for extensions. Currently the dataset is entirely made up of Peruvian pottery. However, with our annotation tools it is possible to easily extend it with artifacts from other cultures, like ancient Greek pottery, or even any kind of textured 3D meshes altogether. In this work we have assumed that patterns do not exhibit any hierarchies or symmetry-based relations, as it is rarely the case for Peruvian pottery. In some cases such relations do exist and could be added on top of our low-level annotations by introducing pairwise relations like is twin of or belongs to. To sum up, we present an annotated dataset of textured meshes with repetitive surface patterns, which can be easily extended with our custom-made annotation tools. Also, we propose fitting evaluation metrics and verified the applicability for the given dataset with 3 different recognition approaches. The dataset as well as the annotation tools and scripts for the evaluation are available at datasets.CGV.theocrats.at/pattern benchmark. Link also in the description.